So what have we done so far? We started out by asking the question, what is the probability of the 11th flip showing tails after we've seen 10 flips with that coin? And we found that the maximum likelihood estimate is a very powerful tool to analyze this, but we also found that it doesn't work so well in a low data regime when we can only observe very few flips. And we found that the maximum a posteriori estimate mitigates some of those problems. But the natural question now is the maximum a posteriori estimate the end of the story? And you can also already guess that no, it's not the end of the story, and we can go even deeper. And to understand why we can go deeper and how we can go deeper, we need to think about what we actually did. So in the beginning we asked this question, what is the probability of the next coin flip showing up tails, given our observations? And during the course of these slides and this video, we also added prior belief, and this prior belief was encoded in the parameters of our prior, which were A and B. So what we're actually interested in is this distribution here. That's what we're interested in. But what we did, or what I did without telling you, when I did the MLE and the MAP analysis, is that I simplified the problem. I reduced the problem to finding a parameter, but this parameter is actually nowhere in here. There's nowhere theta, okay? And the problem is, I reduced the problem to finding a point estimate for this theta. But by doing so, I threw away a lot of information. So we had this posterior distribution. This posterior distribution of the parameter theta given the data. And instead of using the entire information that is in this distribution, I only maximize it. So by maximizing, I throw away a lot of information that is present in our model. And it turns out that if you look at this mathematically, what you would actually like to do is, you would like to introduce the theta like I did in the maximum likelihood case and in the maximum a posteriori case, but you would like to integrate out the entire effect of it. And by doing this, you're using the entire information that is present in this posterior distribution. And that's the big difference, and that's what we can still do. And this approach of using the entire information that is in our model is called a fully Bayesian analysis, because we're using the full Bayesian structure of our model. And that means we're using this distribution P of theta given the data. And we're not only maximizing it, but we're using it entirely. And this is a more complicated, but also a more mathematically correct, I would say, approach to analyzing our random data, our coin flips. Now let's do this fully Bayesian analysis. First of all, we need to rewrite this Bernoulli density, this coin flip density. So the probability of the flip showing the result f given the parameter theta, or more shortly, p of f given theta, is theta to the power f times 1 minus theta to the power of 1 minus f. Okay, this looks a bit complicated, but it's actually quite easy. So first of all, we use this Boolean notation. So instead of saying the random variable f can take on values tails and heads, we say if it shows up tails, it's 1 or true, and if it shows up heads, it's false or 0. So this one here corresponds to tails, and this one corresponds to heads. Okay? And with this convention, what this is actually equal to is theta in the case of tails, and 1 minus theta if heads. Except that instead of a nasty case distinction, we have encoded it into one single formula. And also, if we look at this formula, again, it looks a whole lot like the likelihood term, and it also looks like the beta distribution. And you can maybe already guess where this might be going. Okay, so that's the first step. And then we look at this distribution that we were actually interested in the first place. So this is what we were actually interested in before I started cheating and introducing the theta. Now, what we can do is we can now introduce theta and integrate it out. Okay? This trick always works. This works with every distribution. You introduce a new variable and you integrate it out completely, and the expression stays the same. So this equation is easy. Now, the second step uses two things. First of all, it uses the product rule. So we pull out the theta to the right, that's this part here, and leave all the conditions in there. So that's the multiplication law or product rule or whatever you want to call it. And then if you look at it, what should also be in here is all the other conditions. So that's the data, the A and the B. But what we're saying is we're assuming conditional independence here. So we're saying is if we knew theta, or if we fix theta, then it doesn't matter what the data is or what the prior belief is, because the flip only depends on the value of theta. We don't know the value of theta, but if you fix it, these conditionals become meaningless or useless. So this is a conditional independence assumption. So this second equation doesn't always hold, but it's a reasonable conditional independence assumption. Now we have all the bits and pieces that we need to do this rigorous and more correct fully Bayesian analysis. So remember that on the previous slide, we derived that the probability of the flip result given data and our prior belief is actually equal to this integral, and we didn't have a closer look at this integral, but we can do this now. And we see that it consists of two factors, and the first factor is this nice Bernoulli expression that we just developed, which is this one here. So we got rid of this case distinction and have this nice little expression. And if we look at the second factor, we see that we get the posterior distribution that we've been working with previously in the maximum a posteriori case, and we can just plug that in as well. Okay, so now we have this ugly large integral, but it's actually not that difficult. So what we do is we gather all these terms, we gather all the theta to the power of something times 1 minus theta to the power of something, that's this part here, and we pull out all the constants. And then we recall that we learned this nice trick where we can reverse engineer the result of an integral if this integral looks a bit like a PDF. And that's exactly the case here again. So this again looks like the PDF of a beta distribution. And the reverse engineering trick immediately tells us that the result of this integral must be the second fraction. Okay. This looks quite complicated, but it's actually very, very nice. Because instead of cheating and saying, okay, there is a parameter that actually governs this process of coin flipping and estimating this parameter, we're saying, okay, there is this parameter, but we have no idea what it looks like, so we just use all possible parameters. And if we do that, we can integrate out the biasing effect of this parameter, and we get the true probability of the next coin flip being tails. And it now only depends on the data and our prior belief encoded in A and B. And that's a much more rigorous, much nicer way of analyzing this problem than maximum likelihood and maximum a posteriori. But there's a problem, which is that these integrals are typically very complicated. And with more complicated data sets than coin flipping, these integrals actually get very hard. And that's why people often fall back to maximum a posteriori or maximum likelihood. But you should keep in mind that there's something like a fully Bayesian analysis, and that it's preferable over maximum likelihood and maximum a posteriori if it's doable. And that's not always the case. Okay. And now again, the natural question is that the end of the story? And the answer this time is yes and no. No, because we can go even deeper. Remember that we're still cheating a little bit, so the original question didn't mention any prior belief. So we would need to get rid of this prior belief too, and we would do that by introducing a so-called hyperprior on A and B. So we would choose a prior on the prior. And we could go even deeper and choose a prior on the prior of the prior. And we can do this infinitely often, and this would be in some sense more correct even, but also at some point it doesn't change the result too much anymore. And it's also not that interesting to do all these calculations, so we will stop here with analyzing this coin flipping problem. So we've been talking about all these different approaches, maximum likelihood, maximum a posteriori, fully Bayesian analysis, and about their advantages and disadvantages, and also their connections. Now, we found that the amount of data is crucial to choosing whether you do maximum likelihood or maximum a posteriori. Now, maximum likelihood gives the same result no matter whether you have 5 flips and 1 shows up tails or 50 flips and 10 show up tails. In both cases, we get a maximum likelihood estimate of 0.2 or 1 out of 5. Now, the question is there a quantitative mathematical way of assessing that more data is better? And the answer is yes, there is. And we have to talk about something called sampling complexity. Sampling complexity means how many samples, how complex is the problem, and how many samples do I need to get a reliable estimate. And for the coin flip case, or the general Bernoulli or binary or Boolean experiment case, where you only have true or false events, there's Hoeffding's inequality, which gives us a bound on this sampling complexity. And Hoeffding's inequality looks at the case where your maximum likelihood estimate is off the true result by at least epsilon. So it looks at the probability that you're having a bad result. You would like to be within this margin epsilon, but Hoeffding's inequality asks, how likely is it that I'm outside? And you don't need to remember Hoeffding's inequality by heart, but what you need to remember is that you have an exponential decay here in the number of samples, in the number of coin flips that you're doing. And this justifies why more data is better. You have an exponentially lower risk of being wrong. And that's why it's justified in many cases to use the maximum likelihood estimate.